Hi class, welcome back to our continuations of our lectures in electrodynamics. And again, our reference is Introduction to Electrodynamics by David J. Griffiths. And I recommend you to own this book because this is very helpful in your study of the topic. So let's continue without further ado with our lectures. And we start with methods of images. As you know, if you have a charge that is near a conducting plane, the conducting plane will produce or induce some charges on its surface to counter that charge. Because the charges, as you know, of a conductor, you have excess charges, you have free charges that are moving around or that can move around when it is disturbed. So when you place a charge near a surface or near a conducting material, the conducting material will induce charges on its surface. So like here, suppose a point charge Q is held a distance d above an infinite grounded conducting plane. When you say grounded, it is the potential is zero, or the charge on the surface is initially zero. So here you have this figure, and actually your charge is, your conducting surface extends to infinity here. It extends to infinity in the xy plane. So you have that. So at the conducting charge is located at z equal. The conducting plane is connected at. Is located at z equal to 0. Or the xy plane. This is also xy plane. So the charge Q is located above the plane, and as you know that this is a conducting plane, the electric field below should be equal to 0, and the electric field above is of course not equal to 0 because of the presence of the Q here. So here below E is equal to 0, so hence V also is equal to 0 here. Since the potential on the surface is equal to 0, they should be the same because it is grounded. So what is the potential? So if we if we select a point here, if we select a point somewhere here, what is the potential caused by, what is the potential here? Because essentially the potential here is not equal to 0 because there is electric field above the plane. Below the plane, of course, we know that it is 0. So the potential will be caused by Q, and there will be an induced negative charge here. Why negative? Because it is negative because it is the negative of Q. Because it has to counter the charge near, or the charge Q will attract negative charge on the conductor. So it has to be negative of something. It's negative of Q times a factor, or negative Q prime, say for example. So this V here will be caused by Q, and of course caused by the induced charge R2. Here you have R1, with the distance of R1 and the point I mean, the q and the point would be square root of x squared plus y squared plus z minus d square, and R2 would be equal to square root of x squared plus y squared plus z plus d square, for example, square root of that. So that would be the distance of the two charges. Uh, uh, we actually do not know yet if this is correct. But anyway, let's proceed. So it's not only it's not only this potential, but the potential would be caused by, let's erase this, let's clean this. But the potential would be caused by Q and the induced charge. So, and of course, you know that the potential is following the principle of superposition. So they add up. They add up, but it depends on the sign of the charge. So, what are the boundary conditions here? Again, as I've said, z is equal to 0, the potential is equal to 0 at the surface. This is at the surface. And when you go far away from this charge distribution or from this system, you go away, say for example at infinity, as you go away, the potential must approach to 0 if your distance goes very large. So those are the basic boundary conditions in this particular problem. Or if you have any, you can find 1, 2. But anyway, that is the boundary condition. So you have v is equal to 0 when z is equal to 0, and v approaches 0 as x squared plus y squared plus z squared goes to infinity. Now, we have to find the potential. Whatever process that we use to find the potential is perfectly alright for as long as it satisfies the boundary condition. And it is guaranteed that it is the only potential of the system because of the first uniqueness theorem. For as long as the function or the potential satisfies the boundary conditions. So let's try this situation. We forget about the original problem. We say put two charges. One charge would be up here and the other charge would be up here. The one up here is positive and the other one is negative, and they are both a distance d from the origin. Now, what is the potential here? If you put a point here, what is the potential? So you have to find the distance here and the distance also here and add up the potential. We know that the potential would just be v would just be 1 over 4 pi epsilon sub o q, or say if you have a charge q over r. This is the distance between the point and the charge. The point is where you're measuring the potential, the electric potential. So since there are two charges, you can add up the potential here. But in this case, you have this is supposed to be plus and this is supposed to be negative q, so that it's just automatically put into negative. So here, thus this potential at z equal to 0, 0. So if this is 0, this is just d squared, and this is 0, this is also just d squared. So the potential is 0 indeed at z is equal to 0. How about does this approach 0 as the distance from the origin approaches infinity? Yes, of course, this approaches to 0. So it satisfies the boundary condition. So in this case, your potential V here is satisfying the boundary conditions here, and by the uniqueness theorem, that guarantees that that potential is actually the potential of the system. But in this case, you don't have a conducting plane between the two charges. So we're actually looking only at the upper part of the conducting plane. The lower part doesn't matter because we're just interested on the points above the conducting plane. Here, the points located here. Below the plane, of course, the potential would be 0 because the potential in the plane is equal to 0, and below the plane, of course, there are no charge. So potential would be 0, and only here, or only at these points here, V is not equal to 0. So this potential, therefore, is the correct potential of the system, which we can use on the upper side of the plane. This one. So now, can we get the charge distribution of the plane, of the conducting plane, that is induced by the charge Q? For example, if you put back the conducting plane, remove the negative Q, can we get the charge there? So anyway, I've just said earlier that those are precisely the conditions of the original problem that has been satisfied the potential. So, by the uniqueness theorem, we conclude that the potential of a point charged above an infinite grounded conductor is given by 3.9, this one. So we'll find out the induced surface charge. So the induced surface charge is just equal to, well, anyway, this is the electric field is equal to the electric field above the plane is equal to the negative gradient of the potential with respect to the normal of the plane, and this is just equal to sigma over E sub O, so that sigma of that is in the direction n also. But in this case, our normal direction is equal to z hat. In this case, our normal to the plane is z hat. So we have we can find the charge by this. We can cancel the direction here and just do some algebraic manipulation, and then we get the derivative of v with respect to z and evaluate it to z equal to 0 because the plane is located at z equal to 0. So when you get the partial derivative of v with respect to z, it's just this. So you can do it, you can do the differential derivation of the v, and then when you substitute z equal to 0 here, z equal to 0, z equal to 0, we can then find the area charge distribution, sigma, a function of x and y in this case. So what we will do is that we will integrate this sigma to be able to get the charge induced. We integrate that, but in this case it is easier to integrate in terms of the polar coordinates, where your r square is just equal to x square plus y square, and your dA is equal to r dr d theta. Of course, you can do it also by x and y, but it's more lengthy and a little complicated compared to the polar coordinates. So you can replace xy, x square plus y square with r square, and then you can replace dA with r dr d phi. So you integrate this. The phi has limits 0 to 2 pi. You are covering all the plane, and their dr would be from 0 to infinity. So if you do that, you will integrate this one, your phi will just, your integral of phi from 0 to 2 pi will just be 2 pi, and that will cancel, and your integral of this one, here with respect to dr would just be equal to negative of this one, 1 over that. So if you evaluate that with 0 to infinity, the r, you will get negative q. So therefore, the total charge that is induced on the surface is equal to negative q. And our assumption earlier that we put two charges of q and negative q above and below the origin was exactly right. So anyway, that's it. That's also one way of proving that we have the right potential, electric potential that is just right for the system that we are studying. So what is the force between the two charges, the induced charge and the original charge q? So of course the induced charge would have a distance of negative d, so that they add up to 2d, the distance between two charges. So the force between them would be 1 over 4 pi epsilon sub o q square over 2d square in the z direction. This is negative because the other charge is negative. So that's the force between the two charge. How about the energy? The energy is, you can calculate the energy. It's just the integral of force that dl, or what is this? This is just q times the integral of the electric field that dl. When you put negative, you just change. This is A to B, so this is just B to A when you put the negative sign before the integral. So when you do this, you will actually get by the way, before that, you will when you do that, you will get this. But when you just look at the two charges, you actually will get this one here. You actually would have to get that when you consider the two charges. But note that the electric field, if this is your charge distribution here, the electric field here is equal to 0. But the electric field here is not equal to 0. So only this part will hold a stored energy. So for the entire system, this would be the total stored energy. But in reality, only half of this has the energy. So therefore, half of this one would be the energy above the plane, because there's no electric field. There's no electric field in below the plane, only above the plane. So let's continue. Only half. For the force, it's the same, but for the energy, only half. Why is that? So let's calculate why only half. So here you have the force would be this one. This is the force, and when you do the integration, if you put the negative here, the limits would just be d to infinity, as in when you use the electric field, of course you have to put the negative sign. So when you do that, you will actually get the energy to be this. And look, this is just it. We got the half, not the full. This one is not the correct answer. So this must be the correct one when you use the force. So as Q is moved toward the conductor, the work is done only on Q. It is true that induced charge in the is moving over the conductor, but this costs nothing, since the whole conductor is at potential 0. So by contrast, if 2 point charges are brought in simultaneously with no conductor, work is done on both of them and the total is twice as great. But since you only have one conductor, I mean one charge that is brought from infinity to the point where it is distance d above the plane, so you're only working on that conductor, on that charge. So that's the reason why it's only half. Other images problem. We now take a conducting surface which is spherical. No matter where you put the Q, here, if you put the Q here, that would be the same as this. These are the same because you can always rotate. You can reorient the arrangement. But anyway, let's just take this. So the method discussed earlier can be applied to this surface also. So here you have a charge Q placed outside the sphere, and this should induce a charge, negative charge, on the surface of the plane. On the surface of the sphere. So the negative charge here. But if you take the sphere out, you can replace the sphere out with a charge Q prime here. And of course, the Q prime would be oppositely charged with respect to Q. So Q prime would have some negative charge with respect to Q. Some Q times constant here. So we take a look at this problem. So we will make some guesses on the potential, but anyway, let's take the perfect guess. So we'll choose a charge that is inside, or that is the charge induced by the charge Q, which is Q prime. We take it as this, and then we place it at a distance equal to this. So in this case, you have this figure. We can see from here. So we can, for example, we can draw the sphere here. We can draw the sphere there. So the image charge, this is called the image charge. In the previous example, the image charge negative Q was located negative D with respect to the origin. So it's below the conducting plane. Here the image charge is located at this point. If you recall the mirrors, you have a person here. The image of the person would be here in the same distance as this. So this is, if this is S prime, this is S, your S is equal to negative S prime. That's in the mirrors. Also here, when you have a curved mirror, here, the person would have to be, the image of the person or the object would have to be located here, and the person would be here. So that's in the mirror. So it's the same also here for the image charge, but there are some very little twists that you have to observe. So anyway, this one here you have so again, let's do the sphere here. So the distance, this is the radius is supposedly equal to R. you have r radius. So what happens here? You will have this, since now you have two charges, q prime and q. What is the potential at this point? So the potential at that point would have to be the potential of q plus the potential of q prime caused by q prime. And of course, these are just equal to, this is just equal to this one. By cosine law, you can find this r prime and this r here, and substitute it here. And your q prime would have to be equal to this. Of course, this is just a guess. No method has quantified the image charge to be this one. Well, maybe they got this by brute force. After a long time, they were able to really find out that the q prime is really equal to rq times a, and rq over a, and that's a negative charge, of course. So anyway, the conclusion is, wait, before we, so at the boundary conditions here would be, at r equals r, is the potential 0? Or at r going to infinity, is the potential going also to 0? These are the two boundary conditions that we have to show that indeed the potential is the correct one. So this is what we assume to be the potential. So if you use the cosine law, the potential would actually be of this form. You can calculate that. Anyway, later on in the assessment, you can calculate this, and this is actually the potential that is working on the configurations that we have just talked about. So if r is equal to r, is the potential 0? Or if r goes to infinity, would the potential be approaching 0? So indeed this is satisfied. So therefore this is the potential. And you can also get the induced charge there, and of course the induced charge would have to be this one. Would have to be this one when you get the induced charge. So the force between two conductors is, of course, this one here. The q times q prime over the distance between them is a minus b square. That's the force. This one is the force. And of course the energy would be only outside, because inside the electric field is 0. There's no energy there. But here's a problem here. Find the force on the charge Q. In figure 3.14, the xy plane is a grounded conductor. So this one will induce a charge on the plane. This one will also induce a charge on the plane. So you can find the force. So this one will have an image charge below, and this one also have an image charge below. So anyway, that would be easy and trivial for you. And of course 3.7 would just be the last one that we discussed. And there are other problems here. Problem 3.8, 3.9, and 3.10. You can also do that when you have when you have so much time. And now let's go to solving the Laplace's equation. So we can we had the Laplace's equation here. Equals, we have this as the Poisson's equation. The Laplace's equation is when rho is equal to 0. So let's look at the configuration that we're going to solve. By the way, the Laplace's equation can be solved by methods of separation of variables. And I know that you have heard about that. The method is applicable in circumstances where the potential V, or the charge density, is specified on the boundaries. So the boundaries are very important. Boundary conditions are very important. Boundaries of some region and potential in the interior has to be determined. So let's do an example, and let's solve the Laplace's equation in by separation of variables and in Cartesian coordinates. By the way, let me just check on the first of this slide. So anyway, let's go immediately to the Laplace's equation. Now, this example, we take this example. There are two infinite grounded metal plates lying parallel to each other to the xz plane here. One at y is equal to 0, y is equal to 0, and y is equal to a, the other one. The left end at x is equal to 0, here it's x is equal to 0, is closed off with an infinite strip insulated from the two plates and maintain the specific potential VO of y equals just VO of y. This is equal to the potential there. So there are so many boundaries here. There is a boundary here that extends to there to infinity with respect to the z axis, and there's also a boundary below here which extends to the z axis, of course. both sides of the z-axis, the negative and positive. And there's also a boundary here, a boundary, this boundary, x equal to 0 boundary, but the x is going to infinity here. That's also a boundary, infinite boundary. So there's a boundary on the x on one side, and the boundary on the y, is at y equals 0 and y equals a. You have v equals 0 here, and also v is equal to 0 at those boundaries. Now, we will have to use those boundaries, and we have to find the potential that will satisfy all those boundaries. So in this case, our potential does not depend on z, because z extends to infinity, so it doesn't depend on z, and we have the Laplace's equation to be just the potential would just have to be dependent on x and y, because this is bounded on x on one side and the other is infinite, and this one are bounded on, for the y, you have boundaries on the upper and down parts. So anyway, the z will not, anyway, this would have to be added with z, but the configuration is independent of z, so we can just take out z here. Now, we have this, and these are the boundary conditions. The potential at y equals 0 is 0. At y is equal to a is also 0. At x equal to 0, there's a potential there of the sheet that holds the two planes equal to that. And of course, v should go to 0 as x goes to infinity. And there's no boundary on the z, so we only have this 4 of these. So now we can find v as a function of v x y, and we can take this v to be a product of two functions, x of x and y of y. So now we have this, and then we substitute this v to here, to this, and then we find that we have this, we can rewrite that into that one, and then we divide by the functions xy to arrive at this equation. And now looking at this, this is just a pure function of x, and this is just a pure function of y. And by the laws in calculus, if you have two functions added or subtracted from each other, which have different arguments or variables, then the two must be constant. So we can rewrite this as, a constant C1 and constant C2, for example. But they would have to be equal in magnitude. The other one would have to be negative. So in this case, you have you can set this as k square and this one as negative k square, so that you can rewrite this as this one, and you can rewrite this one as this one here. But why do we choose negative and the other one is negative and the other one is positive? Or we can put negative here or positive here, it's perfectly okay, but we have to choose the correct signs, because, like, for example, on the x side, we have to choose k to be positive, because there is one boundary on the x that tells you that it's infinite. So it has to have an infinite value at some. I mean, it has to have a value at some point at infinity, but of course that value should be approaching to 0. And on the y side, you have two planes, and the two planes here would you have a boundary here. You have two planes as boundary. So here you can use sine functions or cosine functions, so that you have to choose the negative here, and this one is exponential. We'll give you an exponential solution for this differential equation, because exponential would be appropriate if your boundary extends to infinity, and in this case one side of the x extends to infinity, the other one is blocked. So you can choose the positive k here, and positive k squared and the negative k squared for here, because this one will give you sine and cosine. So x would have this solution, and the y would have this solution, and you can find the product to get the v. And so a would have to be 0 for x, because if you extend to infinity, if you extend x to infinity, this would blow up, and at infinity the potential should be 0. So we have to set this equal to 0, so that we're left with this, and we absorb the constant b to c and also d, so that we can write our potential to be this one here. And here at the boundaries of the y, boundaries on the y, because you have two planes, you have two planes at y equals a and at y equals 0, the potential would be 0, both of these. So if cosine k times 0 is equal to 1, and this is not equal to 0, so you have to set d equal to 0 too, and so you're only left with sine ky. So therefore your potential would have the form this one here. So that's the form of your potential. Now let's find out let's further apply the boundary conditions. And the only way that sine could be 0 is when your Ka, or when your argument here Ky, is equal to some integer times pi. Your Ka is equal to an integer times pi, and so your K would have to be n pi over a. Your K would have to be n pi over a, where n goes from 1 to 3 and so on. So you have to make a decision on which constant has to be positive or negative, because that will also affect your solution. So for example, if had you chosen this one to be negative and this one positive, then your solution would be a mess. So you also have to choose the signs. So anyway, that's how you do that. The separation of variables has given an infinite set of solutions. Why infinite sets? Because you have a lot of n. Your n can can take a value of 1, 2, 3, and so on. So definitely you have an infinite set of solution. And for each n, you will have each potential. You will have a different set of potential. So if you want to find a general solution, then you can do this by superposition, and that's the linear combination of all the potentials, where the alphas are arbitrary constants. So if you take the Laplacian of this one, you can also take the Laplacian of the others, and of course that's equal to 0. So and the V, so here you have this is actually equal to C e to the n pi over a x negative sine n pi over a times y. So you have then the general form of the potential, where n starts from 1 to infinity. How would you find Cn? You can find Cn. So of course your VOY is equal to x equal to 0. So when this is equal to 0, so your VOY would just be this one here. So how would you find the Cn? What is the Cn? You can do it by Fourier streak. The Fourier streak here. What will you do with a Fourier streak? You can multiply here. You can multiply and integrate. You can multiply sine n pi y over a on both sides here. So you have to multiply on this side and on this side, and then integrate with respect to dy. This one are orthonormal sets. You have a special identity for that, and of course you can just integrate this VO. If you can set VO to be a constant, then you can take that out of the this out of the integral if this is a constant. But in this case you have a dependence on y, so it's safe to put inside. This one is the identity for here, for that one. So this can be simplified. So you can now find n, and so that's the Fourier streak that you have to do in order to find the. So Cn would have to be, so if you do that, would have to be this one here. So as a concrete example, suppose that at x equal to 0, the metal plate with constant potential V has a constant potential V, for example. You can take the VO out of the integral, and so this is the expression that's left inside the integral, and this one will have would have an integral that looks like that. And of course this is just equal to this one. If n is even, that would be 0, and if n is odd, this would be 4 v sub o over n pi. And so finally, with Cn equal to that, then we can have an expression of the V. This is kind of a long potential, but it's nice looking, and n here would have to be 1, 3, 5, 7, and so on, because the even terms would give you 0. So that's the potential that you can get. And if you plot that, you will have this one. You have the plot for V over V sub O with respect to X over A and Y over A. It's a nice one. You can try this on your computational lab and get the plot. You just have to plot this one. The only problem is that you have an exponential. I think you have this can be found in C++, I guess. So you can plot that, and on the if you plot only this and this one, you can have a two-dimensional plot between this and this one. It will look like this. So you have just for the first 100 terms of the series. So actually this one here, you can further simplify into a closed form. You can find the identity, and it's equal to that. You can find identity, and you'll be able to get this. So we have a complete potential, and the series we have shown also orthogonality of each element in the series. So a set of functions f and y is said to be complete if any other function fy can be expressed as a linear combination of them. So we can express that as the potential as a linear combination, so it's a complete set. You may have encountered this completeness in some other subjects that you had, especially in mathematical physics. You have to discuss that. And also orthogonality, we exploited that in the Fourier streak, that if you integrate an fn and fn prime of y dy, this is equal to 0 if n is not equal to n, if n prime is not equal to n.